Hello everyone, my name is SeungminKim. In this presentation, I will be guiding you through Chapter 7 of ISLP, focusing on technique for moving beyond linearity, specifically regression spline and smoothing splines. Let's start by looking at this graph showing CO2 concentration over the past 800,000 years. If we try to fit a simple linear regression model, imagine a straight line, red line here. Could we confidently say it captured the underlying pattern well? Clearly, the answer is no. This data exhibits significant nonlinearity, complex ups and downs, that a linear model fundamentally cannot represent accurately. In the real world, relationships are rarely perfect linear. While the linearity assumption is often a useful approximation, there are many cases where it falls short. To address this, we need more flexible modeling approaches. This capture explores several methods like polynomial regression, piecewise function, regression spline, smoothing spline, and generalized additive model that offer this flexibility while aiming to preserve interpretability as much as possible. Our first approach to handle nonlinearity is polynomial regression. The idea is simple. We extend the linear model by adding polynomial terms of the predictor. The equation looks like this. By increasing the degree, we can create increasingly complex nonlinear curves. The purple line in the plot below shows a 14-degree polynomial fit to the age-weighted dataset. You can see it captured the nonlinear trend reasonably well in the middle range. However, polynomial regression has a significant drawback. High-degree polynomials often exhibit erratic behavior, especially near the boundaries of the data. Look at the right end of the purple curve. It shoots up dramatically. This kind of wild behavior is unrealistic and makes polynomial unreliable for extrapolation. To overcome this, we can consider methods that use multiple simpler curves joined together. This leads us to piecewise polynomials. Instead of one complex curve, we divide the range of the predictor into segments and fit a separate polynomial in each segment. The point where the segments connect are called nodes. This equation shows a piecewise cubic function with one node as Ci. The plot shows an example. However, if we fit the polynomial in each piece completely independently, we often get discontinuities, sudden jumps at the nodes, as seen here. This is problematic for two main reasons. First, it's unrealistic. Most real-world phenomena change continuously. Second, it creates instability. Tiny change in x near the node can cause huge jumps in the prediction. To fix the discontinuity problem, we introduce splines, which are piecewise polynomial with constraint ensuring smoothness at the nodes. The simplest spline is a linear spline. It's a piecewise linear function that is constrained to be continuous at each node. We can represent this using basis function. The model is yi is beta 0 plus beta 1 b1 plus beta 2 b2 plus ... where the basis function are b1x is xi, bk plus 1 xi is xi minus xi k plus. The term xi minus xi k plus is a hinge function. It's 0 until xi reaches the xi k, and the increase linearly with a slope of 1. Right side graph shows how this hinge function looks like. Adding this hinge function allows the slope of our overall function to change at each node, creating a continuous piecewise linear fit, like the one shown. We often want something smoother than just connected lines. A cubic spline is a piecewise cubic polynomial that is continuous and also has continuous first and second derivative at knots. This ensures a very smooth curve without sharp corner or abrupt change in curvature. We can represent it using a truncated power basis function, where xi minus psi k power 3 is 0 until the k naught psi k, and then increases as xi minus psi k power 3. The magic is that these basis functions are constructed such that any linear combination of them automatically satisfies the constraint at the k naughts. Because this xi minus psi k power 3 and its first second derivative has zero value in x is psi k. A cubic spline with k naughts uses k plus 4 degree of freedom. The graph shown an example. Notice how smoothly the curved band compared to the linear spline. Similar to high-degree polynomial, standard cubic spline can exhibit high variance near the boundaries of the data. The natural cubic spline addresses this by adding an extra constraint. The function must be linear beyond the boundary knots. Look at the plot. The red natural spline is much more stable at the edges than the blue cubic spline, with narrower confidence band. This linearity constraint reduces the degree of freedom. Because of constraint, beta 2 and beta 3 become 0, and beta k plus 2 and beta k plus 3 be a constant, which make the cubic and quadratic term to 0 at right boundary. So a natural cubic spline with k knots use only k degree of freedom. Regression spline require us to choose the number and location of knots. Smoothing spline offer a different, more automated approach. The goal is to find a function g hat x that balances two things, fitting the data well and being smooth. This is achieved by minimizing the objective function. The first term is the RSS, pushing the curve towards the data points. The second term is the roughness penalty. It penalizes the wiggleness of the function, measured by the integral of its square derivative gmx. The parameter lambda controls the trade-off. If lambda is low, we prioritize fitting the data, potentially leading to a wiggly overfit curve. If lambda is high, we prioritize smoothness, forcing the curve toward a straight line. Now, let's apply this concept to solve problem set 7. The problem asks us to sketch the shape of the curve g hat that minimize the smoothing spline objective function under different scenario for lambda and m, where m is the order of the derivative in the penalty term. In case A, lambda is infinity and m is 0. Since lambda is infinity, the roughness penalty term completely dominates. To minimize the objective function, the roughness penalty itself must be 0. This requires integral gmx squared dx equals 0, which implies gmx is 0 for Rx. With m is 0, this means gx is 0. So the function gx must be identically 0. The sketch is simply at flat line at y is 0. In case B, lambda is infinity and m is 1. Again, lambda is infinity forces the roughness penalty term to the 0, meaning gmx is g prime x is 0. If the first derivative is 0 everywhere, the function gx must be a constant, say gx is c. Now we need to choose the constant c that best fit the data. minimizing the RSS term. The constant that minimizes this is the sample mean of the yi. So g hat x is mean y. The sketch is a horizontal line at the average y value. In case C, lambda is infinity and m is 2. Following this same logic, lambda is infinity requires g 2 prime x is 0. If the second derivative is 0, the function gx must be a linear function ax plus b. To minimize the RSS term under this linear constraint, we simply perform a least square linear regression. The sketch is the best fit straight line through the data points. In case D, lambda is infinity and m is 3. Here, lambda is infinity requires g3 prime x is 0. If the third derivative is 0, gx must be a quadratic function, ax squared plus bx plus c. Minimizing the RSS term under this quadratic constraint means we perform a least square quadratic regression. The sketch is the best fit parabola through the data points. In case E, lambda is 0 and m is 3. Now, lambda is 0 means the roughness penalty term completely disappears. The objective function is just the RSS. To minimize this with no constraint on smoothness, the function gx must pass through every single data point exactly. This is called an interpolating function. The sketch will be a very complex, wiggly curve that hits all the data points. And I'll introduce one way to find this complex curve. This Lagrange interpolation finds the n-degree curve which passes through given n plus 1 points. To explain precisely, this pi function get value 1 if x is xi. If not, this function get value 0. And our function px expressed as sum of yi pix. So this function has value yi in xi for Ri. This is unique function and degree curve which pass through given n plus 1 points. This is end of problem solving, and so far we've seen how useful splines are for modeling the nonlinear relationship between a single predictor and a response. But the utility of splines doesn't stop there. In fact, splines serve as the core building block for a more powerful and flexible modeling framework known as GAMS. A GAM extends multiple linear regression by allowing nonlinear function for each predictor, while maintaining an additive structure. Now, the important point here is that each of these function fix can be modeled using the spline we just learned about. This allows us to capture complex nonlinear effects for each predictor variable individually, while the additive structure still allows us to interpret the effect of each variable. For example, this graph shows the result of applying a GAM to a wage data. Here, F1 year shows the trend in wage over time. F2 age shows the nonlinear relationship between age and wage. And F3 education shows how wage differ across education level. Each plot represents the unique effect of the specific variable after adjusting for the effect of the others. This interpretability is a key advantage of GAMS. Smoothing techniques like this are still being actively researched, and I would like to introduce one of them, P-splines. The core idea of P-splines is a combination of two key elements. The first element is B-spline. Our model P-spline represents a complex data trend, like this blue line as a sum of several mountain-shaped B-spline basis functions. However, If you only use B-splines, the number of splines determines the smoothness of the curve. More spline leads to a less smooth, regular result that can overfit the noise. The second element which solves this problem is the penalty. P-spline imposes a constraint to restrain the difference between neighboring elements of the coefficient vector. In other words, it balances the goodness of fit to the data, y be alpha squared with the smoothness of the curve lambda, d alpha squared. Here, increasing the lambda value increasing the penalty, resulting in a smoother curve as shown in figure. So, how are P-splines different from traditional smoothing splines? The key difference lies in how the penalty is applied. The traditional smoothing spline uses a continuous derivative penalty on the curve itself. Specifically, the integrated squared second derivative for this penalty to work mathematically. The curve must be at least cubic. This means the curve's degree and the penalty's order are strongly coupled. A P-spline, on the other hand, applies a discrete different penalty not on the curve, but on the P-spline coefficient. This is why the paper states it is not true that the difference penalty is just an approximation of the derivative penalty. It is fundamentally different. This fundamentally difference gives P-spline serves powerful advantage. Flexibility is first one. As just mentioned, P-spline allow you to freely combine any degree of P-spline with any order of the penalty. They are independent. Second one is simplicity. You don't need to worry about optimal knot placement. You can just use even spaced knots, which is a nature and easy choice. Third one is robustness to overfitting. You can set a generous, even excessive number of B-splines. It is not possible to have too many B-splines because the penalty will control the smoothness. First one is computational speed. The B-spline basis matrix and the penalty matrix are both sparse. Thanks to this, data series with billion of observations can be smooth in a fraction of a second. Last one is extensibility. P-splines are easily extended to other statistical frameworks, such as generalized linear model, mixed model, and Bayesian approaches. This is end of my presentation. We study several ways to represent data's nonlinearity and how this approach improved. Thank you for listening.